So today we are going to dive into hypothesis testing. There are a few steps in hypothesis testing. First of all, state your null hypothesis. That's a hypothesis of no difference, no change. And alternatively, state your research hypothesis. That's what the investigator believes to be true generally. But it is the alternative to the null hypothesis. Now, we say a null hypothesis is no difference, but no difference from what? Your null hypothesis could be that the proportion of participants in after-school activities who are girls is 0.5. That's another way of saying there's no difference in the proportion of girls and boys. You could say your null hypothesis is that the mean National Assessment of Educational Progress scores on mathematics for 8th grade Native American students in South Dakota is 262. And that's another way of saying that it's not different from the national mean for Native American students. So state what your null hypothesis is. Second, collect some sample data and determine whether the sample data support your research hypothesis or your null hypothesis. For example, if you're testing from the population mean, you would collect sample data and you would get the sample mean. Next, you want to set up a decision rule to decide when to believe the null versus the research hypothesis. That's going to depend on the level of significance, alpha, which is usually set at 0.05. If the probability of getting the obtained test certificate, say the mean you got for your sample, is less than alpha, say less than 0.05, you reject the null hypothesis. Otherwise, you don't reject the null hypothesis. Finally, after you've gone out and you have set a decision rule, you've collected some sample data, now you're going to get a test statistic, say a Z or a T or F, as you'll find out later, but you're going to get a test statistic, like a Z value, and then you're going to see what's the probability of that test statistic. Say, if Z is greater than 1.96, then based on that probability, you will draw a final assessment as to whether your alternative hypothesis is likely true, given the observed data, or whether your null hypothesis is likely true. Now, as your textbook says over and over and over and over, you can't prove the null hypothesis isn't true, right? It may be that 1 out of 100 times you would only get a result like this if the null hypothesis was true, but it could be that 1 out of 100 times. What you conclude is the null hypothesis isn't very likely. It's sometimes confusing to people because we talk about p-values in two ways. One, p-values represent the exact significance of the data, like you'll get a probability, you'll get a result this large or larger by chance 3% of the time, and then the p-value, which we also call alpha, this little Greek letter here, p-value is also the smallest value where we would still reject the null hypothesis, like 0.05. So what you're looking at is the probability of the value obtained less than your alpha. And if it is, reject your null hypothesis. Now, there are two types of errors that come up when you are doing hypothesis testing. Now, the first one is the type 1 error. And we talk about that a lot in statistics. The type 1 error is when you reject the null hypothesis, when in fact the null hypothesis is true. So like I said, 1 out of 100 times, you're going to get that p equals 0.01 result. And the reason that there's a difference between those two means is just chance. You just happen to have the smartest kids in the sample that got your intervention. So that's a type 1 error, and your probability of a type 1 error is alpha, 0.05 or 0.01 if that's what you chose. Then the other type of error is type 2 error, and that's when you say that the null hypothesis is not rejected, but in fact the null hypothesis is false. So we have an intervention in a school. We're now having everybody do homework after school instead of taking it home. And we conclude that it made no difference in children's math achievement, but actually you're wrong. It did make a difference. We just didn't reject the null hypothesis, maybe because we didn't have a large enough number of people in our sample. And actually, that's something that we should talk about later because it can occur a lot in small rural schools that we just don't have very many people. But anyway, those are two types of errors. If the null hypothesis is false and you reject it, then that was the correct decision. That was not an error. If the null hypothesis was true and you don't reject it, again, that was the correct decision. There are two types of tests. We mostly talk about two-tailed test. I almost always would push for doing a two-tailed test. It's usually very difficult to justify a one-tailed test. A one-tailed test is saying none of this over here is possible. Say you have this new intervention that now we're going to have kids do homework after school instead of at home. And my hypothesis is that there's no difference between the two conditions between doing it at home and doing it in school after school. And the alternative hypothesis over here is that kids will do better. I'm saying there's no possibility that we could consider that students would do worse. And I think that's very, very hard to justify. But the only time I can think of is that we were talking about, say, if children were severely abused, is it possible that they would be doing worse or there'd be no difference? I can't imagine severely abusing children would make them do better. But that's the only possibility I can think of, really. There aren't very many times when you can really justify a one-tailed test. And one of the reasons that researchers who are not very ethical would like to do it is, let's say this is the area under the curve. This is the probability of you getting a significant result, right? So we have 2.5% over here, 2.5% over here, so it adds up to 5%, and 95% in here. Anything that falls in here, we're going to fail to reject the null hypothesis because we say, well, 85, 70, 30% of the time or whatever, it could have occurred by chance. What if we don't have a two-tailed test? Then all this part here gets moved over. And now all of a sudden, things that would not have been rejected are. So it's kind of cheating. It's moving all of the possibility of things, of something having occurred by chance, over here. And that is kind of hard to justify. Speaking of Z&T, where does that come from? It's the probability that you would get this value for the mean or proportion or difference between means if your null hypothesis is in fact true. Let's say, and I will post this, we can do some simulations, that the population is actually evenly divided, boys and girls. What's our probability? How many times are we going to get a proportion of 0.6 if this is in fact true? Now, if the true proportion of the population was 0.5, you'd most often get 15 successes out of 30 attempts. And there's a substantial probability you'd get 14 or 16, and a close to zero probability that you would get 0 successes out of, and we say success as being whatever particular event you are interested in, result you are interested in. So if you were interested in how many girls there are in after-school programs, a girl being in your sample would be a success. And if it really is 50-50, then in the population, if you pulled out 30 kids, you should have pretty small probability of 30 of them being boys, or 0 of them being boys. Now, as a human, reading results, a lot of things can be done by a computer these days. We will look later at how to do, say, a t-test using Excel or how to do a z-test using Excel. But one of the most important things for you is knowing when to reject the null hypothesis. That will be in another video. Coming up, look forward to it.